Welcome back to our discussion of thin film PV concepts. In a previous video we looked at transparent conductive oxides, which are an important class of materials for thin film solar cells. Now we will discuss an alternative device structure to the conventional p-n junction, namely the pin junction. The learning objectives for this video are therefore to get familiar with the pin junction. We will discuss what a pin junction is and why it is used in thin film solar cells. Additionally, we will discuss the concepts of substrate and superstrate solar cells. We will start the discussion by recollecting the two mechanisms for charge carrier transport in solar cells, diffusion and drift. Diffusion is a process whereby particles tend to spread out from regions of high particle concentration into regions of low particle concentration. So if you have a cross-section like the one shown here, with all the charge carriers concentrated on one side, the charge carrier density profile will resemble a block diagram. As a result of random thermal motion, there will be a net movement of charge carriers to the low concentration region, creating a more distributed concentration profile. The current generated by, in this case, electron diffusion is described by this equation. Here Q is the elementary charge, D is the electron diffusion coefficient, dN over dx is the concentration gradient. The second charge carrier transport mechanism in solar cells is drift. Drift is charged particle motion in response to an electric field. Basically, if a negatively charged electron is placed in an electric field, it will experience a flux in the opposite direction of the field, so to the positive end. A positively charged hole will experience a flux in the direction of the electric field. Now in terms of a Venn diagram, the electric field flows from the positive n-type region to the negative p-type region, causing a drift of electrons towards the n-type and a drift of holes towards the p-type. The current resulting from the electron drift is described by this equation, where n is the electron concentration, mu is the electron mobility, E is the electric field strength. The diffusion length of the minority charge carrier, indicated by L, is equal to the square root of the diffusion coefficient and the carrier lifetime. The diffusion length can be interpreted as the typical distance minority carriers diffuse before they recombine with a majority charge carrier. It therefore does not make sense for the thickness of the absorber layer to exceed the diffusion length, since electrons farthest from the n-doped layers and holes farthest from the p-doped layer would no longer be collected. The diffusion length for crystalline silicon is about 300 micrometers. The thickness of a crystalline silicon absorber layer is therefore limited to about 300 microns. Some materials used for thin film solar cells, such as amorphous silicon, has a much higher defect density than crystalline silicon and therefore a much shorter diffusion length. The typical diffusion length of amorphous silicon is only 100 nanometers up to 300 nanometers. Hence, the transport of charge carriers in a thick absorber cannot rely on diffusion and must rely on drift. Thin film silicon solar cells are therefore sometimes referred to as drift devices. Consequently, amorphous silicon solar cells are not based on a p-n junction, but rather on a pin junction. This means that the intrinsic layer, meaning a layer that is not intentionally doped, is sandwiched between thin p-doped and n-doped layers. While the intrinsic layer is several hundreds of nanometers thick, the doped layers are only tens of nanometers thick. Between the p and n-doped layers, a built-in electric field is created across the intrinsic layer. This figure shows the p, I and n layers when they're not connected to each other. In this situation, the Fermi level in the p layer is closer to the valence band and the Fermi level in the n layer is closer to the conduction band. For the intrinsic layer, the Fermi level is in the middle of the band gap. When the layers are connected to each other and the system is in the dark and under thermal equilibrium, the Fermi level has to be the same throughout the junctions. This creates a slope over the electronic bands in the intrinsic film, which reflects the built-in electric field. Note that there are no majority or minority charge carriers in the absorber layer, since the intrinsic layer is undoped. Drift is therefore solely responsible for charge carrier transport in the absorber layer. Due to the electric field, light-excited electrons will move down the slope in the conduction band towards the n-doped layer, and holes will move up the slope in the valence band towards the p-doped layer. Inside the p-doped layer, on the other hand, the holes are the majority charge carriers and the dominant transport mechanism is again diffusion. The same goes for electrons in the n-doped layer. Because of the low diffusion lengths inside the doped layer must in fact be very, very thin. Let's take a look at a solar cell with a pin junction. In thin film silicon, holes have a significantly lower mobility than electrons. The p layer is therefore used as the window layer, which is the layer positioned first in reference to the incident light. In this case, the generation rate of electron-hole pairs in the intrinsic absorber layer is higher close to the p layer, and more holes can reach it. Between the p layer and glass substrate, a TCO layer is deposited to facilitate lateral charge carrier movement to the electrodes. The p layer is followed by the intrinsic absorber layer and the thin n-doped layer. Finally, the back contact is deposited, sometimes preceded by a TCO or silicon oxide layer. The doped amorphous silicon layers have a high defect density and therefore an extremely small diffusion length for its majority charge carriers. As a consequence, unlike traditional solar cells, photo-generated charge carriers in the doped layers of a pin cell cannot be separated and collected. Light absorption in doped layers is therefore considered to be a loss, a parasitic loss, as it does not contribute to the generation of a current. Consequently, the doped layers in a pin cell have a very specific set of requirements. In order to maximize the amount of light reaching the absorber layer, the reflection at the interface of the window layer should be minimal. To that end, the refractive index of the p-doped layer should be equal to the geometric mean of that of the TCO layer and I layer. The n-doped layer, on the other hand, should reflect as large a fraction as possible back into the absorber layer. Secondly, the doped layer should be transparent to incident light to minimize parasitic absorption by the doped layer. This could be achieved by having a doped layer with a high bandgap energy so that it is transparent to a large fraction of the incident light. Moreover, a high bandgap energy also benefits the built-in potential in the cell, which affects the cell voltage. Finally, the doped layer should be conductive enough for charge carriers to easily move through the material to the electrodes. In other words, the doped layer should have adequate transverse conductivity. Balancing the optical and electrical properties of the doped layers is a delicate process that can strongly influence the device performance. Note that in this picture we have assumed that the solar cell is processed in superstrate pin configuration. Superstrate indicates that the supporting structure on which the solar cell is processed is positioned first in reference to the incident light. The yellow-orange arrows indicate here the direction of the incident light. The red arrow indicates the deposition direction. In superstrate devices, the device is generally processed in pin order. In substrate devices, however, where the mechanical substrate is positioned at the back in reference to the incident light, the device is processed in NIP order, since the p layer should preferably be positioned at the front of the device. In these devices, light first encounters the layer that is deposited last. As you will see in the upcoming video lectures, a PV module based on CIGS generally has a substrate configuration, while thin film silicon technology, like amorphous silicon on glass, usually has a superstrate configuration. Also note that the devices shown here are actually multi-junction PV devices, which we will discuss in one of the upcoming videos. Now time for a recap. We discussed the two transport mechanisms for charge carriers in solar cells, and we saw that for thin film amorphous cells, diffusion cannot be used. We discussed that the designation NIP or PIN indicate the order in which the layers are processed, while substrate or superstrate indicate where the supporting structure is positioned in reference to the incident light. Finally, we looked into the device structure of a superstrate PIN cell and considered the specific requirements of the doped layers in a PIN junction. In the next video, we will look at another important concept for thin film PV, namely light trapping in solar cells.